Right, finally, we get to a mixture consisting of 3 moles of hydrogen peroxide, 2 moles of oxygen, and 5 moles of hydrogen placed in a 5-liter container and heated to 900 Kelvin. It's allowed to reach equilibrium. We're asked to determine the equilibrium amounts of each substance if KEQ is equal to 0.0076 at 900 Kelvin, and then we're provided with the balanced equation. Now, this question is the trickiest on the paper. It's the meanest, and I'm very, very much hopeful that such a question would not appear on HSC. It's niggly and mean-spirited, I think, but it could appear. There's absolutely nothing to prevent this question from appearing. It's fair, it's just a bit mean-spirited, I think. It's a good classroom activity, but maybe not a good exam question. However, I'm not on the exam committee, so I don't get to decide what will be asked. So initially, let's convert our number of moles and the volume of our flask into initial concentrations. So the initial concentration of hydrogen peroxide is 0.6 moles per liter, oxygen 0.4, and hydrogen 1. Now this question is unlike all of the other questions that we've seen in that it is not immediately clear which direction this reaction should proceed in, or at least it's not immediately clear to me. In order to work that out, what I'm asking here is, what do I put in that change row? Am I saying that I will decrease the concentration of peroxide and increase the concentrations of the others? That's the assumption that I've almost always made in the past. In this case, that's an assumption that leads me down a very, very dangerous path that gets ugly very quickly. So instead, I remember, please, that KEQ for this particular reaction at this temperature is 0.0076. So it's small-ish. Now, find the reaction quotient for this reaction in its initial condition. So that means write out the expression exactly the same way, concentration of the products divided by the concentration of reactants. Only remember that we can't call that KEQ because it won't be at equilibrium initially. So instead we call it capital Q. That's called the reaction quotient. So there's the expression for the reaction quotient. Here are those initial concentrations substituted in, and I find that the value of that expression is 0.6666, so on, 7. Eventually we have to round it somewhere. Compare these two numbers. You see that this one is much larger than that one. That's like saying there are too many products for this system to currently be at equilibrium. So because Q is larger than KEQ, the reaction will proceed to the left. For a nice diagram that illustrates that, go back to your textbook on page 75. That's way back in chapter 2 or 3, I think. Now, with that new information, the reaction proceeds to the left. Let's have another go at our icebox. And we end up with an icebox that looks like that. Notice the sign in front of X for oxygen and for hydrogen is negative, where the sign in front of X for the hydrogen peroxide is positive. And that's the opposite of what we would typically expect to see. But it is in keeping with this earlier analysis that this reaction has to proceed to the left in order to establish an equilibrium. So the concentration of hydrogen peroxide, H2O2, is going to have to increase, which is why there's a plus X. Right. Now, I know the value of KEQ at this temperature, and I need to find the value of X so that I can find those equilibrium concentrations. So I sub in and I evaluate the quadratic, ending up with 2 possible values of X. So in the first case, if X is 0.99495, I will end up with a negative concentration for oxygen. So just like in the previous question, this can't be a solution. So that means that my solution must be X is equal to 0.397445. That leaves me with an equilibrium concentration of oxygen equal to 0.00256, an equilibrium concentration of hydrogen equal to 0.603, and an equilibrium concentration of hydrogen peroxide equal to 0.997. And those values are, again, slightly different than the values that have been previously published.